The patient's current systolic blood pressure should be obtained as part of the complete cardiac exam to compare with the pressure gradient of a mitral insufficiency in order to estimate or verify left ventricular pressure and stage the severity of mitral insufficiency. High pressure gradients suggest or verify hypertension, which may require additional or different treatment. This dog's blood pressure was 158 millimeters of mercury, and the pressure gradient was 154.7 millimeters of mercury. Normal pressure gradients a little lower than systolic blood pressure suggest mild or moderate mitral insufficiency. Pressure gradients higher than the patient's measured systolic pressure indicate severe mitral insufficiency. This dog's blood pressure was 165 millimeters of mercury, but the pressure gradient was 199 millimeters of mercury. Let's try to understand pressure gradients. A pressure gradient is the difference in pressure between the pumping chamber and the receiving chamber. In this case, the pumping chamber is the left ventricle and the receiving chamber is the aorta. For example, the normal pressure gradient of the aortic flow through a normal aortic valve, or any other normal valve, is about 2 to 5 millimeters of mercury. That means that the pressure in the left ventricle, the pumping chamber, is 2 to 5 millimeters of mercury higher than the pressure in the aorta, the receiving chamber. A small amount of pressure of the left ventricle is lost due to friction of blood passing through the valve. If the patient's systolic blood pressure has been measured at 120 millimeters of mercury, then the pressure in the left ventricle could be estimated to be approximately 122 millimeters of mercury. 120 plus the pressure gradient of 2 equals 122. Bear in mind, calculated pressure gradients are not necessarily accurate. They are usually underestimated. Therefore, if the patient's systolic blood pressure is measured and the maximum flow velocity of the aortic valve is measured, a pressure gradient can be calculated and the pressure of the left ventricle can be estimated. In this case, the maximum velocity is 112 centimeters per second, and the calculated pressure gradient is 5 millimeters of mercury. The patient's systolic blood pressure was 118 millimeters of mercury. Therefore, 118 plus 5 equals a left ventricular pressure of 123 millimeters of mercury. If mitral insufficiency is present, the pressure gradient of the regurgitant jet can also be used to estimate left ventricular pressure and can be verified by measuring the patient's systolic blood pressure. In this case, the left ventricle is still the pumping chamber. The aorta is still the receiving chamber, but now the left atrium has become a second, abnormal receiving chamber. The pressure gradient of the mitral regurgitation can now be used to verify that left ventricular pressure is normal or elevated if systemic hypertension is present. Pressure gradients are calculated using the Bernoulli equation as follows. Pressure gradient equals convective acceleration plus flow acceleration plus viscous friction. Convective acceleration is equal to 4 times the flow velocity after the valve squared minus the flow velocity before the valve squared. Flow acceleration is negligible in most cardiac diseases. Viscous friction, in this case the normal viscosity of the patient's blood, in most cases is also negligible. Therefore, flow acceleration and viscous friction are excluded from the equation to form a modified Bernoulli equation. Both the Bernoulli equation and the modified Bernoulli equation contain convective acceleration in the calculation. In normal valves, the squared velocity of blood flow before the valve is negligible. Therefore, a simplified Bernoulli equation is created, where pressure gradient is equal to 4 times the flow velocity after the valve, that is, in the receiving chamber, squared, or 4 times maximum measured velocity squared. This simplified Bernoulli equation is automatically calculated by most ultrasound machines when you measure maximum blood flow through any cardiac valve. The simplified equation does not account for flow acceleration, viscous friction, or flow velocity squared before the valve. In this example, a velocity time index measurement is used to give a maximum velocity and a pressure gradient. The calculated pressure gradient of the continuous wave Doppler measurement of a mitral insufficiency can also be used to help stage the insufficiency. Remember, pressure gradients are usually underestimated. The pressure gradient of a mitral insufficiency should indicate the patient's left ventricular pressure if aortic stenosis is not present. The pressure gradient of the mitral insufficiency should be a little less than the patient's measured systolic blood pressure. In mild and moderate stages of mitral insufficiency, the patient's measured systolic blood pressure will be very close to the calculated pressure gradient if aortic stenosis is not present. In severe mitral insufficiency, the large defect of the mitral leaflet allows blood flow in the left ventricle to accelerate prior to passing retrograde through the mitral valve. Flow velocity in the left ventricle before the mitral defect is no longer negligible, but the simplified Bernoulli equation does not account for this change. In this case, automatic use of the simplified Bernoulli equation by the ultrasound machine results in an overestimated pressure gradient that is higher than the patient's measured systolic blood pressure. Therefore, a calculated pressure gradient higher than the patient's measured systolic blood pressure indicates a severe mitral insufficiency in the absence of aortic stenosis. This dog's blood pressure was elevated at 165 millimeters of mercury, but the pressure gradient of the mitral regurgitation was 199.8 millimeters of mercury. Note that pressure gradients may also be overestimated in cases of anemia, where blood viscosity is decreased. The simplified Bernoulli equation does not account for changes in blood viscosity.